In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony.
Hello and welcome to Aether Cosmology, episode 64. Tonight we have a Christmas Eve special, the Null hypothesis for flat Earth. And we'll just jump right into what that is and what it means exactly. And if anyone has any questions, comments, or concerns throughout the Prezi, feel free to interrupt at any time and ask questions, because this is for everyone to learn together. So if anyone has any questions or needs clarifications, feel free to jump in. All right, so a new way that I'm going to be arguing flat Earth and presenting the information and the data that we have is going to be from a position of our strongest mutually exclusive proofs and evidences, where the deciding factor is mutually exclusive, because you can't have two things that are simultaneously true while they oppose one another. So the way that we'll do that is we'll take the academic approach of using the null hypothesis method, which is used for PhD research and getting your, making your thesis or whatever. So regarding using the sky to prove the shape of the ground, we all know the formal position from the globe is that the shape of the ground is derived from the sky, right? Everything in the sky happens because of Earth curvature, stars deviate, sunsets, etc. So my argument is that you can't use the shape, or you can't use what's going on in the sky to determine the shape of the Earth, but you can use that information to tell you what the Earth, what the shape isn't, right? So the null hypothesis is going to be the thing that we're going to assume to be true. And then we're going to try and find evidence against it or for it. And we're also going to have a competing hypothesis that's going to be our alternative hypothesis. And if we find enough evidence that we have falsified our null hypothesis, then we reject it, and we reject it in favor of the alternative hypothesis. So we'll go over what my nulls and alts are here in a second. But just to add some more clarification here, like I was saying earlier, the null hypothesis and alt hypothesis, which will be henceforth referenced as H0 for the null and H1 for the alt. These are mutually exclusive, so they both can't be true. While you can't prove your hypothesis, you can fail to falsify it. So you know how they say in science, oh, we can't 100% say we proved it, but well, this is why, this is like the logic behind this. We're going to look at evidence to try and falsify the truthfulness of it, of the assertion. So failing to reject your null hypothesis indicates that your data was not sufficient to overthrow it. And you'll have all that presented and laid out so that people can read what your information is and make their own conclusions about it. And ideally, you'll have a statistical analysis of the different evidences put forward, and then you'll answer in sigma confidences on whether or not your null hypothesis is true. Now, that part of the presentation hasn't been added yet. This is just kind of a rough layout that I'm going over, but this will be formalized and put into like an actual paper format that'll have the included sigma analysis in it. All right, so another quick example here to really drive this home is this is very similar to the you can't prove a negative fallacy, like where someone's position will be that unicorns are real and the other person will say that they're not real. Well, you would have to prove that they're real because you can't prove that they're not real. So it's the same kind of thing. So your H0, if you were to do this analogously, go ahead. Oh, what's up, Danielson? You're hot micing a little bit, brother. So if you were to do this out analogously to the proving a negative fallacy, you would say your H0 would be unicorns don't exist, and the H1 would be unicorns do exist, and these are mutually exclusive, so they both can't simultaneously be true. And if you were to falsify the null hypothesis, you would have to do that by providing at least 4 unicorns for statistical significance, because the first unicorn could be some genetic anomaly. The other two could be, the same thing or some other thing. So you have to have 4 for statistical significance. So that's kind of the way you look at it. You don't go all or nothing. You have to have the sigma confidence to it. So that's the additional component to it that makes it, that adds credence to it. So in regards to Earth being flat versus a globe, my H naught is going to be the Earth is planar, and measurements of curvature are dependent on the position of celestial bodies. So this follows that the Earth is planar, and any curvature perceived will be optical. H1 will be the Earth is globular, and measurable curvature is independent of celestial bodies. So we'll often get into debates and you'll hear the phrase, well, the Earth is measured flat. Well, the Earth is measured curve. Well, I measured curve. I measured flat, right? Who did what? Well, what is the flat or curve in reference to? Suppose I take a theodolite and start looking at a mountain at a distance and it's not as big as it should be. Where did the mountain go? Did it go behind a physical Earth curve? Is it tilting away like a reciprocal zeni? Or is it just an optical compression due to perceived visual space? How can we determine the difference between the two? Well, we're going to have to examine some mutually exclusive incidences to determine that. And that's what we're going to be doing moving forward. So for the H1, it's going to logically follow that the Earth is physically shaped as a globe. That's going to give us actual physical Earth curvature that's going to cause obstruction to celestial bodies. So we're going to be looking for evidence for that in our analysis. And as we go through the proofs, we're going to start off with the map that we all use, the old graticule. And this is very important because what do maps represent? What are they used for? Can they be used to deceive us? Are they 100% accurate? Do they tell us everything we need to know? Let's take a quick look here at a ABC news piece regarding maps during wartime in World War I believe this was. All right, we'll take it away, ABC newscaster.
When you think of the world, this is probably the map that comes to mind. It's everywhere. Atlases, school walls, even Google Maps. It's also very, very wrong, and it's been distorting our view of the world for centuries. This is a Mercator projection. It's one of the most common projections used for world maps. This guy, Gerardus Mercator, created it in 1569 to help with ship navigation. The map was revolutionary because it straightened both lines of latitude and longitude, which was great for sailing. All you had to do was draw a line to where you wanted to go on the map and follow your compass. But to make a navigation-friendly map, the projection distorts land masses the closer they are to the poles. That gives us the wrong idea about the relative size and maybe even the importance of some regions. This creates what some map makers call the Greenland problem. This is Greenland on Mercator's map. It's huge. Here, Greenland is bigger than the entire continent of South America. The same thing happens with Alaska. The state looks bigger than the entire country of Mexico. The farther land is from the equator on a Mercator map, the more stretched out it looks. In reality, South America is 8 times the size of Greenland, and Mexico is actually bigger than Alaska. For the same reason, this is what 2,000 miles looks like on a Mercator map, but so is this. It's the same distance, the fault is in the map. This happens because map makers have to rely on mathematical formulas to project the surface of the Earth, a sphere, onto the surface of a map, a plane. Calculus and complex algebra eventually improved map projections, yet the Mercator stubbornly remained a popular general world map. While it made for a great navigation map, it was also being used as a geographic map in classrooms and atlases. The distorted view of Earth's land masses in a Mercator's projection became how people saw the world. Mapmakers and geographers were not happy. Everything started to change in the mid-20th century. There was a world war, and more airplanes were being used than ever before. Editorials published in the New York Times in the 40s called for the Mercator to be discarded and reminded readers the grossness of its errors should not be forgotten. In a series of orthographic maps in 1942 and 43, Fortune magazine declared the Mercator is no map for global war, and it was a dangerous map to use in studying global strategy. An expose on cartography life published around the same time called the Mercator a mental hazard in a war that is plotted on great circles across the land and sea and through the air. Perhaps nowhere was the rejection of Mercator's projection more apparent than with Richard Eads Harrison's illustrations. The architect turned illustrator for Fortune magazine created maps truly fit for a world dominated by flight, offering revolutionary views of the planet as World War II raged. With Harrison's maps, it was clear just how obvious the United States' isolation was, or how many neighbors Europe had. It was at this time that maps were starting to take on a new use: persuasion.
This union of 12 nations became known as the North Atlantic Treaty Organization, or more simply, NATO.
Suddenly, maps became a convenient way to show just how threatening Germany's neighbor Czechoslovakia was, when it really wasn't, or how imperative it was to fight communism, or how threatening other countries were to the USSR. A transverse oblique homolographic map does wonders for showing how close and how threatening the USSR really was in this Times Atlas map. Eventually, a German historian created what he said was a revolutionary map projection that he marketed as the solution to the Mercator. For Arno Peters, the Mercator represented Western imperialism. His new projection, with a more prominent Africa and South America, was meant to emphasize what he called the Third World. Reactions ranged from cautious amusement to outright hostility. Peters had trashed the cartographic community in writings promoting his map, and his version really wasn't even that original. A Scottish clergyman named James Gall had created virtually the same thing in 1885. Eventually, the American Congress on Surveying and Mapping stepped in and had a resolution. The organization and 6 other cartographic groups urged map publishers, the media, and government agencies to stop using rectangular depictions like the Gall-Peters and Mercator for general purposes. The answer to the Greenland problem was not a new rectangular map, but instead non-rectangular projections like the Mole-Wide or the Eckhart 4. The media picked up the resolution. There was a column in the Washington Post, and it even made it to the front page of the Wall Street Journal. Right there. The Gall-Peters hasn't gone away. Boston Public Schools recently said it will now use the Gall-Peters in classrooms to quote-unquote decolonize the curriculum. But it's not like the Gall-Peters is replacing all maps. You can find different types of maps everywhere. The UN logo has an azimuthal projection, and a good homolocene is in the background of CBS's evening news broadcast. But if you're really concerned about how to look at the world, you should probably just buy a globe.
All right. So if you want to know the proper interpretation of the spherical coordinate system and its projections, it's asserted here that you should probably just buy a globe, because that will accurately portray the continents and sizes and distances and everything. And that's kind of, true, because that projection, it is a hemispherical coordinate system that's overlaid with a southern hemisphere, and the merger of those two makes a sphere. So it does have the aesthetically pleasingness of the symmetry for the distances and whatnot. But the fact of the matter is that coordinate system can be projected invariantly over many different projections. And as long as you use the distance preserving aspect correctly for the transfer or for the projection that you're using, you will have the exact, that map will represent the exact same thing in terms of distance wise and all that. So what I mean by that is all of these shapes here are all equally valid. They could all represent, because they're all representing the same thing with respect to the latitude and longitude system, because the latitude and longitude system is just the positions of the stars with respect to the vernal equinox. So if all these projections are equally valid, how can we determine if the Earth is a sphere or if the Earth is a plane that's been mapped with 2 hemispheres of vision? Well, first we'll have to discuss optics. So we'll get into curved visual space, and this is actually logarithmic versus Euclidean, because what we found was that there's linear portions of your vision And then there's extreme curvature where, anyway, it's best represented logarithmically rather than hyperbolically. But anyway, we'll get into what that exactly means now. So you'll see how in the horizon, for example, the best or the easiest one to conceptualize is that train tracks converge at the horizon. If we saw in Euclidean geometry in parallel lines, we would never see these converge. Now, in reality, the 3D spatial field is Euclidean, right? The objects have a exact positioning in 3D space, and then your visual field, though, is logarithmic, where you're going to have different curvature factors at different distances, and at the horizon, everything is going to be brought together, like at a focus point. So that's what creates your dome of vision. That's what brings these parallel tracks in Euclidean 3D space together in your visual optical space. That's what does that for these shadows. When you have shadows during sunsets from a mountain, they'll say that the Earth is being curved, and because of the Earth rotating away from the sun, it's casting a shadow on the clouds underneath it. But when you go on top of the mountain, you'll find that this is just an optical illusion. The shadow is being cast down by the sun over top of it. So this is this is also evidence against the idea that a sunset is caused by Earth curvature. So this will be added to the sun, or to the shadow set list here. But this is a optical illusion produced by perspective, and when you go to the top of the mountain, you'll find that the sun is never below Earth's surface due to curvature, due to you rotating away from it in any way like that. So next up is the further substantiation of the use of your dome of vision. So a lot of people like to argue that this is a made up concept, that flat earthers made it up, or that it doesn't exist, et cetera, et cetera. But here we have from the History of the Royal Society, when they were making the longitude measurements, what they did was they had a telescope aimed at the horizon. They would take measurements, they would tilt it up, and they would tilt it all the way 180 degrees back towards the other horizon behind them, and they would create a literal dome star map. So this was used by them in the 1860s, and probably even a little further back than that. But yeah, so that's where it started. And then we have Dr. Carl Lundberg, on his paper on curved visual space and hyperbolic geometry, where he was thinking that curved visual space was curved at a constant rate. But as it turns out, it's logarithmic, but we can get into that a little bit later. But one of the points he makes about curved visual space and optics is in Euclidean geometry, in Euclidean 3D space, take celestial bodies, for example. The sun is 860,000 kilometers wide, and the Earth is 24,000 kilometers wide. And we're in the center of the sun, so the entire sky that is lit up by the sun should just be the sun. It should be the biggest object in the sky. It should be the entire sky. But it's not. We see the sun as a focal point that's 0.53 arc seconds in the sky, so half a degree in size in the sky. And also, the stars that we see, the other astronomical bodies, are said to be, thousands of times larger than our sun, that's claimed to have a physical size of 860,000 kilometers. And we see these as little tiny dots. And he's saying that this was impossible unless, you're optically converging the light from these bodies into these focus points. Because if you were to assert this through Euclidean optics, none of this would work. It doesn't make any sense. So he makes that argument about it. And this is a guy who doesn't have any stake in the matter, right? Like, he's not a flat earther. He's not trying to convince anyone. This is just like logical deducting to support his position. And then we have this awesome find by the Aether Cause librarian, who found this old and new astronomy book, where it's noted here about seeing in a dome and having a dome of vision. We have the celestial sphere here that's intersected by a fundamental plane, and then you would have all your celestial coordinates would be mapped to this. So Let's read here what he has to say about this. So overhead is the dome of the heavens, which is so far it is determined by the actual positions of the visual bodies of the heavenly orbs or by the blue of the sky or the clouds, has in reality no definable shape, but which may be geometrically regarded as a hemisphere around a center. Oh, no way. Someone, oh, Andrew, you're hot micing, brother. This is not intended. The natural idea of the observer, whom the dome of the heavens appears to have somewhat a flattened form, and the horizon being between them, 4 times away as the region overhead. Oh, interesting. So we can like see an entire hemisphere in the sky relative to our latitude in the north. So basically, you can see stars from the north, like from Polaris to the equator when you're in the north. And considering a cloudy sky, we have to remember that we rightly understand what we see is actually the curved surface at which we are looking at is much flatter than it is. We mistakenly attribute it to the dome shape of the heavens, whereas in reality, the curvature is no greater than the curvature of Earth itself, in which the ordinary conditions are imperceptible. So, Earth curvature comes from the sky and the position of celestial bodies, and we see in a dome, but that's not to be mistaken for an actual dome or a dome of vision. This is due to the Earth curve. Okay. All right. Well, let's see what Gauss has to say about spherical excess and curvature. So we're going to learn more about relating this newfound optical phenomenon to spherical excess and a radius of vision corresponding to, I don't know, the radius of Earth, and having an optical equivalence between the two, which would make referencing positions of the stars or terrestrial observations and measurements without referencing a radius, which is positions of the stars, it would make it impossible to distinguish the cause of why things get smaller or disappear in the distance. So this is from Gauss, or I'm sorry, this is from Direct Measurement of Curved Visual Space. The notion of intrinsic curvature was introduced by Carl Gauss in a seminal paper dating back to 1837. Although the theory is arcane to psychophysicists, some of its consequences are relatively easy to grasp. Intrinsic curvature differs from extrinsic curvature. A flat piece of paper remains intrinsically flat when you roll a cylinder or a cone, although its extrinsic curvature may change. Intrinsic curvature is evident that certain non-Euclidean properties or figures are from a certain non-Euclidean properties or figures. One example treated by Gauss concerns the sum of the interior angles of a triangle made up of geodesics, the shortest arcs, in Euclidean straight lines. So Euclidean lines on a sphere. This is going to give us spherical excess. In the Euclidean plane, the sum is 180 degrees. Any deviation is called angular excess, which reveals the intrinsic curvature of space. The excess is proportional to the area of the triangle. The excess per unit area is a measurement of the intrinsic curvature. Notice that its physical dimension is 1 over the square. Thus, the inverse of the square root, the absolute value of the angular excess, has the dimension of length. Gauss showed that it simply equals the radius in the case of a spherical surface. So what he's saying here is if you go to try to measure a triangle over distances on Earth and you measure excess in that triangle, so you measure over 180 degrees, that excess, you can establish a relationship as a distance, and that's going to be equivalent to the radius. So your excess over the area measured is going to be equal to the radius of the sphere. So you can derive 3959, the radius of Earth, from spherical excess measured from optics or from Earth curvature. They would both give the same result. So here we'll take an example here of Earth curvature and how small these measurements are. So here's a very simple example. Consider the geographical triangle from Amsterdam to Boston to Cape Town. In this triangle, there's an area of 83,700,000 kilometers square. From Boston to Amsterdam, there's 5,568 kilometers. Cape Town is 9,914 kilometers, and the sum of the triangle is 234 degrees, 28 minutes, and 3 arc seconds. This differs appreciably from 180 degrees. The Earth is significantly curved. The specific spherical excess is 0.0507 seconds of arc per kilometer squared. According to Gauss, this equals the curvature averaged over the triangle. 1 over the square of this curvature equals 6,378 kilometers, which is 3959 miles or thereabout, which is the radius of the globe. Thus, we obtain the radius of Earth or from the direction of triangles as seen from other areas on the triangle. Notice the specific curvature is small. For instance, excess in an equilateral triangle with sides of 1 kilometer is only 0.002 seconds of arc. Locally, the Earth is flat. So what'll happen is you can never measure the Earth as being curved. Locally up to 1 kilometer on an equilateral triangle is going to produce an imperceptible amount of curvature that you couldn't make any distinguishes about. But what you can do is you can introduce a large survey, add things together, and add up little deviations from referencing the stars and get spherical excess that will be the equivalent of the coordinate system that you're using. So if you're trying to map the celestial sphere to the ground and make that the radius of the Earth, you're going to need those two to be equivalent. So what you'll do is you'll go measure positions of the stars, which we'll get into here in a second, and then you'll make corrections to those on the ground, and you'll call the difference in those corrections due to spherical excess. And that excess will be computed to back to a specific radius. So that's how that's exactly how this is done. And we'll get into geodetic surveying as we continue, now that we've covered the optical equivalence between curved visual space and Earth curvature and the relationship with the stars. So we have also everything in the sky in regarding these celestial bodies. What we're going to find out is that they're apparent objects. They're always in motion. We always see their apparent position. We never see their true position. Their true position is an idealized snapshot of the sky on the vernal equinox using the law of cosines to make triangles, to use the ratio of the angle to establish a distance based on the elevation angle to the star. And then they go underneath that star and they start to take zenith measurements of it. And what they found was that they could never, no matter how hard they calculated or tried, they could never go underneath a star, level out their telescope, and have it be directly in the center of the crosshair. They always have to make a correction to it, and we'll get into why that is here in a bit. But this is just adding to the fact that they're apparent. So this is a manual from a solar panel guide from the 60s, and this is showing how the sun moves across the sky in your field of vision, in that dome of vision that was referenced earlier. And here we have NASA referencing the same about the position of the moon and how it's apparent, so you can check that out. So these are mainstream references. This is part of accepted cosmology. Everything in the sky is an apparent position. All right, so now we'll get into the measurements of Earth curvature. Now that we've went over, we can't distinguish optically if Earth is curved or if our eyes are curved, right? So now we're going to look at how they told the difference between the two when they made maps. So astrogeodetic surveying goes into exactly what I was talking about earlier, where it's the combination of making measurements on the ground, making horizontal measurements, and then comparing those measurements to zenith angles of the stars, and then doing mathematical transformations to put those stars in the correct position, or in the correct ground position, and then taking the difference of how much they would have to correct their telescope to get that star in the center of it when they look up. And they're calling that excess, Earth curvature. That's what it all comes out to. So that's referenced throughout Arc of the Parallel, all geodetic surveying where they do that, the big surveying that was done in India. All of that is full of astronomical corrections because you can't measure Earth curvature without having it be with reference to without being in reference to something else. And in this case, the only thing we have is the positions of the stars. So what we're finding out here as we continue is that Earth curvature is not measurable without it is not independent of the position of the celestial bodies. It's dependent on them actually. So here we have from a surveying paper that says, the true dimensions of Earth must be known to the exact for the computations and positions, and it is evident that these determinations must be necessary to carry out the true geodetic surveying. And all computations must have been previously known for the Earth's dimensions, etc., right? And the reason for this is because the coordinate system is math, right? Like it's perfect. It's 360 degrees. It's a spherical coordinate system and all that, right? But the sky and how we perceive everything in the motions of the bodies in the sky isn't always perfect. And this is how they reconciled the two to make the most accurate coordinate system available is they had to make timing corrections to these. So now everything becomes about positions of the stars with respect to specific timing. So now they're looking for transits over certain spots where it's intersecting with meridian lines, so they can more accurately map the spherical coordinate system that they're using from the sky to the ground. And assuming, having a hard radius defined like this is extremely important. This is why when we say, okay, we falsified the radius value, so we falsified the globe. Well, that would be because this entire coordinate system is based on the exactness of this, like just to even use the coordinate system to the accuracy that it's used at. All these values have to be exact. And then they have to be assumed and then built upon. Then you have to use ratios of them. Otherwise, none of this works. And if they were more upfront about that, it would be nice. But it's like, obfuscated and made to seem separately. Like we have these units of measurement that are independent of the coordinate system, even though all units of measurement are fractions of the spherical coordinate system that's used. So they're fractions of a terrestrial meridian, which makes them basically in relation to sky miles. So everything is in relation to a nautical mile. In terms of units of measurement and how they do all this. So to make all this work and tie it together, it has to be exact. So again, this is just positions may be apparent in astronomical accordings to the corrections applied for aberration and the subscript adopted for the combinations of all reference and positions. So again, this is just more correcting observations to meet ground positions. Now, what we found out through examining the history of light and trying to figure out if the Earth is in motion, some experiments that were proposed showed that starlight already comes in at an angle with respect to a stationary Earth. But what that means, more importantly, for the surveying aspect is the reason why when these people take an elevation angle to a star and follow the cosine and get the distance to that star and then go directly underneath it and look up, the reason why they could never get a direct true position, even though they have this nice coordinate system in reference to true positions and exactitudes, the starlight already comes in with a horizontal drift to it. So it's always going to be displaced and slightly off. And instead of acknowledging that and accepting that, they call the correction to that Earth curvature. So it started off with a guy named Arago who had a crystal prism and a half covered telescope. And when starlight entered the telescope, what would have to happen if the starlight came in parallel as the Earth moved through it, there would have to be a further correction angle as the light hits the refractive medium and is slowed down because the Earth has more time to move through it. And the importance of this is because, like I was saying earlier, the way that they derived, the way that they were using the elevation angles and cosines was to complete 90-degree angles and assume, and to do this, they have to assume that there's a true position of the star and that it's sending a light ray in perfectly parallel. And when they look up, because they're at a direct 90-degree zenith and they're perfectly level, they're not going to have any refraction, and they're going to be able to get the most accurate positioning on this due to their interpretation of cosmology. And that's not real. Like there's no, their idealized calculations and conceptualization of how they could use their calculations turned out to not be true. And part of that was started with Arago showing that when he put the crystal prism over the eyepiece, there wasn't any correction angle necessary because the starlight is already coming in at that angle where it's deviated from where they expect it to be perfectly, and it's not due to any Earth motion. So then this was repeated again by Airy, who did the same thing using a zenith mount, where he could rotate the telescope 180 degrees to itself and take measurements and take the mean of that to ensure accuracy. And what he found is that there was only when the water was added, there was only a difference of 0.8 arc seconds. So when you add a refractive medium, what this is telling us is that the starlight already comes in with that horizontal drift component to it, rather than us moving through it. And that changes the dynamic, because that means that their idealized interpretation of parallel light rays and all that is false. It's not possible. It's not possible to begin with. It's a fundamentally false premise to begin with. And then to apply that to the sky and then assert that, you have dominance over it because of Earth curvature is preposterous. So here's what the zodiac would look like over an azimuthal equidistant projection. So this is just to kind of show the equivalence between the two, because mostly we see this in reference to in reference to a globe. So now we're going to get into some deflections of the vertical. So we were talking earlier about how they take these zenith measurements and they have to do a correction. They have to tilt their device or assume the difference from the idealized calculation, and the reason is due to Earth curvature. So they say that the Earth is an ellipsoid. It's an oblate spheroid. So parts of it are flat, parts of it are curved. So when they cosine up and they get underneath that star, well, the reason it's not at the zenith is not because light already comes in with a drift to it and there's no actual true position. It's that the Earth is actually curved, or it's flat in that area, and you need to make an adjustment to compensate for that. So they went around and did surveying and calced all this out and came up with the ellipsoid. So the ellipsoid is based off of these zenith corrections in reference to horizontal measurements where the two didn't line up, and they were rectified by assuming that this was due to an offset in the shape of the Earth. So we'll read a little bit here. The first evidence of the deflection of the vertical. So Johann Soldner therefore suggested building an observatory in Africa to close the equator, or close to the equator, for the moon observations and conducting the precise measurements of the arc. Pierre Simon Laplace and von Soldner introduced the idea of flattening, which must be described as a function of latitude and longitude. However, the facts were known about Earth curvature at the beginning of the 19th century and were simply additional results for the measurement of the symmetrical rotation of the figure of the Earth. And from here, they started introducing those deflection of the vertical corrections to make everything line up with that. Because like I was showing earlier, the moon, the sun, all of that is apparent. Because such measurements cannot be double checked. So this goes into the timing real quick for everything. So the specific timings for the transits to line up with the longitudes and latitudes where they intersect. So first, because of such a measurement could not be double checked, there was no way to assure its accuracy. Therefore, measurements were repeated, often in hope that there were no or very few statistical errors. Second, one statistical error cannot be excluded from this type of measurement: the reaction time of the observer, or the so-called personal equation. Girling visited his colleagues in Göttingen and whatever that is, and determined that the personal equation of each observation by comparing the meridian observations of stars and by noting the time of passage of a pendulum. He could thus estimate not only the statistical error, but the offset and the reaction time. The offset turned out to be surprisingly large, which led Girling to mention earlier to Gaub and in question of the former longitude determination of the island Heligoland, Greenwich, and in Paris. So again, this is the in reference to, you know, the sky dictating the correctness of the coordinate system on the ground. There's no one's out here measuring Earth curvature or establishing it. All measurements are in reference to the sky at all times. Otherwise you just have nothing. How flat's flat, how curved is curved, in reference to what, as they say. So here's a little diagram of what these corrections look like from a side view here. So we got our ellipsoid, and that's going to have, when they're looking up and they're saying they have to correct to that for the deflection of the vertical. Well, now they're going to introduce an additional correction to be in line with a gravitational model. So now they're going to introduce a gravity vector, because after they did their first ellipsoid for the surveying to see how much deviation there was on the ground from the perfect celestial sphere of an infinite radius, they took they went back and did more surveying to get more accurate with it. So in the arc of the parallel, halfway through that, they realized that their ellipsoid measurements were not lining up with their current measurements. And they were like, well, how do we introduce another reason to tilt our instruments a little further? Now, this is where they said that there was gravitational anomalies. And when you drop a plumb bob, it's not actually going to the center of a ball, and it's actually offset due to a gravitational anomaly. And the difference from the true plumb going to the center of the ball is noted as the gravitational vector correction. So they're introducing another deflection of the vertical in reference to maintaining a perpendicular relationship with the gravity vector. Very cool stuff there. So it's just like introducing unlimited corrections to make the ground fit your conceptualization of the sky. And as long as you, as we established earlier, as long as you have a specific amount of spherical excess that you can get out of that you can make your horizontal measurements compute to, you can make the ground reference the sky and always get back to the radius of your coordinate system, which is 3959. All right, so another instrument that's used for optics, and this in particular applies to long distance observations, long distance laser measurements, etc., is they will introduce a refraction coefficient, which is basically just a ratio of the radius of the Earth and how far you're seeing something. So they can increase the radius to make the Earth more flat, to basically co-opt any observation to make it comport to a globe. So any observation with laser or just optical measurements and all that are automatically equivalent to a globe or a flat Earth with a limit of vision. So we're going to have to use we're going to have to come up with a different way to falsify Earth curvature other than an optical method, because we have an equivalence here between the two. And then now that the accepted method of confirming globularity is to use the coefficients established as a ratio between the radius and how far you're seeing something, and these gravitational vector and ellipsoid corrections to the stars, is we're going to have to come up with a different way to falsify it now. All right, so we have a couple of notes here. There was one from Australia where they were saying that the deflection of the vertical is as far as 30 arc seconds. And then in here, in this paper, they were saying that Throughout the new datum that they apply, there's like a discrepancy of 6 arc seconds all around, and nobody seems to care about these things because either way you slice it, it all ends up comporting back to a globe, but you have these like insanely egregious corrections that aren't due to a curvature that was physically measured, right? It's due to the position of a star being different than you expected, and then assuming that the Earth is curved due to that. All right, so to give a quick reference on these measurements like arc seconds, degrees, and all that, what we're looking at here is fractions of 360 degrees. So 1 arc second is 1/3600th of a degree. So if you can imagine breaking down a circle, instead of breaking it into 360, you can break it down into 3,600. So just really fine sections in between 1 and 2 degrees. And these and the spherical excess is like you would think like, oh, if they're measuring a spherical excess, it must be like much greater than 180 degrees, right? Because there is a ball, like, I don't know, I always conceptualized it as being like, I don't know, like 190 degrees or something crazy, but it's like 180.00000027 or something like that. I think Shane has the exact numbers, but it's like, it's ridiculous, but it's all based off of those compounding deflection of the verticals and geoidal gravitational potential corrections on the assumed curvature and radius value to make the coordinate system useful. Oh, thank you. He just pulled it up. I'll put that up on the screen for the boys real quick. Thank you, sir. Yeah, so mostly it's actually measured sub 180 degrees, and then after corrections, etc., references to ellipsoids, geoidal corrections, they get just over 180, and they're like, oh, there's where the ball's at. So this only exists.
Here's one that's calculated 180.0172. That's the proper way to get it to. So.
Thank you, sir. Thank you. So yeah, this is all in reference to positions of the stars, though. Unfortunately, no one's out there measuring an actual, curvature per area or anything like that. All right. So yeah, this is just more on refraction coefficients and how they apply those all willy-nilly to make anything comport. So we have an equivalence there. So we're not gonna argue terrestrial observations. Because of the equivalence between the two, it could go either way, unless you reference the stars. So if you make your dependency of curvature on the stars, then you can use that to bolster your claim. But as our claim is that the curvature should be measured independent of the stars, and that hasn't been substantiated yet. So our null hypothesis is still looking pretty good. So for the RZA masterpiece, what we find out is with these refraction coefficients and these minuscule measurements, the refraction coefficients and what's the other thing? The deflection correction the air margin ends up actually being larger than the deflection of the vertical in some of these cases. So it's like we have these imperceptible numerical values that are dictating curvature over long distances. It's insane, where the air margin and refraction coefficient are larger than what's claimed to be measured. And then they use that as the evidence. That's preposterous.
That's not reification at all.
Yeah. So here's a side overview of the merger of the two models. So the ellipsoid model. So that was the first iteration of going around, taking terrestrial measurements of the stars, taking those zennies and measuring the difference between the two. And then the geoid is the gravitational potential offset, which is when they went back and took more accurate measurements and tried to stitch everything together. They were, as we observed earlier, they were sub 180 degrees. How do we get to 180 degrees, boys? Gravitational potential corrections. And then we'll count that difference as spherical excess, which will comport to our radius as noted by Gauss in the 1830s or whatever. All right, so here's a nice visualization of what's going on. So imagine you're on the ground here terrestrially, and you're taking your observation of this object over here. And you're like, oh, how far below is it below my theodolite? What's the angle there? oh, is it adding up to 180 or over 180? And then once they got their measurements, right, they have to reference them to something. So now after they've got their measures, they look up and they take zenith angle measurements and they start going, okay, why is this star not here at the specific time of year when it's supposed to be directly overhead? Well, okay, let me deflect my vertical, transform that to the ground, and see what happens there. So they've got their idealized calculations for the sky that make a perfect triangle, and then they got their measurements on the ground that don't compute to the idealized position of the triangle in the sky, and now the difference is Earth curvature. When looking through,
super important right there.
yes, and when looking through the arc of the parallel, if you Control F corrections, you can find all of the corrections and assumptions they do, but more importantly, you'll see that it's always in reference to the astronomical phenomenon. So what's going on in the sky is dictating the accuracy of their horizontal measurements on the ground. So I think this is just more in reference to celestial coordinates. You know, just like I said, they're always comparing that for surveying. So if anyone has a measurement of a theodolite, for example, right? If there's a guy going around with a data set of looking at mountains and he says, hey, I'm not making any assumptions. I'm just taking measurements. When I look at this mountain, it's smaller than what's expected. How is it below my theodolite eyepiece? What's going on here? This wouldn't work on XYZ. This is the only reason I can come up with is it matches the globe. That's fantastic. As soon as it matches the globe, doing air quotes, we've got a radius and we're talking about the celestial sphere. We're now talking about reference to the sky. We're no longer talking about a data set that's not in reference to anything. So now we're going to, now that we've established the connection between all of these and how they're related and how you can't just have a measurement, make no assumption and have it comport to the globe without it already being in reference to the sky in the first place to comport to the globe, we're going to determine how we can distinguish the difference between the two coordinate systems. So one coordinate system is going to be dictated by physical Earth curvature, and the other one's going to be optical, where all celestial phenomenon always takes place above the horizon. So just as we were just about to wrap up the surveying and coordinate system and map section here, and exit into the mutual exclusivity interpretation of the coordinate systems, or the projections of the coordinate system, sorry. So here we have the royal decree from 1776 from the jolly old King of England, who says, hey lads, we got this new coordinate system from the longitude boys, and everyone has to use it. Otherwise they're going to have to pay a sum of 20 pounds, per time they don't use our map. And when I'm talking about coordinate system, I'm talking about the new map. So the new latitude and longitude that we're all using today, this was dictated to us by royal decree, and fines were imposed to any who would not capitulate to it. Now on the back end of this decree, there was they posted like a bounty hunter section where they were like, hey, we've actually got some problems with the coordinate system and we want to improve the accuracy of it. So we're actually hiring astronomers and mathematicians to go on voyages to circumnavigate around Britain, so that such that two ships can circumnavigate in opposite directions to one another using the same coordinate system and stars, and help us figure out these corrections to get everything on the up and up so this can be done. And they put out a bounty that would be equivalent to $2.5 million today, I think, something like that. It was like 10,500 gold shillings or shekels or something. So this is what was decreed and imposed upon us, and this is the function of the coordinate system, is so that two people can use it to reference the stars to accurately navigate. And this is from the Supplemental Nautical Almanac in Astronomical Ephemeris and American Ephemeris. And what this is basically, this is the book for the reference ellipsoid. People were wondering, like, oh, how did you guys come up with these corrections? What did you do? This book is all about traversing the land and making measurements with an assumed celestial sphere model with a radius of, I forget the value, But anyway, it's the deviations on the ground are then computed, and the difference of that, is what determines like the oblateness of this area and that area. So just to show you that they're always using that same system where it's the fundamental plane. You have a hemisphere of vision. Everything is mapped to the relevant hemisphere that you can see in. All right. Okay, so summary of direct measurement evidence. So what we saw, what we went through, was that no one is measuring Earth curvature. They're always referencing the sky. Anyone that claims to be just making a measurement has to, in some way, reference the sky to make an argument with their data. Otherwise, they just have nothing. If it doesn't match anything or anything that's already been established with reference to the sky, then their measurements are nothing, and they're not arguing for anything until they tell you that it comports to the radius of the globe. And then you can then go through how that was established through assuming idealized positions of stars and the deviations from them, and then attributing that to Earth curvature and making, uniform corrections using two different reference models, a gravitational potential model and an oblate spheroid model, to come up with offsets for that. So, who knows, right? So when we get into mutually exclusive evidence, though, we have shadow sets. So what do I mean by shadow sets? If the Earth is a ball and you're rotating away from it, and physical Earth curvature is obstructing the light of the sun such that it's causing a sunset, and it's causing a shadow, like it's the reason that you're not getting light anymore, right? Then the behavior of shadows is going to be a certain way, and we're going to look at a model of that. But before we do, quick shout out to Taboo Conspiracy and the gentleman who made this model. I can't remember his name, sadly, but shout out to those who put this video up, and then shout out to Man of Stone, who has a physical demonstration of how this simulation plays out in reality. So we'll take a look at this. So on a globe, what is predicted for physical Earth curvature is that an object casting a shadow will cast a shadow that's higher than itself. For example, these two pillars will cast a shadow on this wall over here, and they will exceed the height of the pillars themselves. And this window that's casting a shadow on the wall behind it will eventually rise up above the window itself. And as that's happening, there will be an abrupt end to the shadow, because as you're turning away at 15 degrees per hour, there's going to be a hard cutoff due to Earth curvature, and that's going to create a shadow that's going to sweep across the land and immediately take everything out and make it dark. Now, the flat Earth position, which is that the celestial bodies are never underneath your feet or never go below the horizon, is that the object casting a shadow, the shadow will never exceed the height of the object casting it. And what would happen specifically for the instance of the window here is it would cast a shadow on this back wall that will rise up, and then it'll stop before it'll slow down as the sun gets further away rather than going under you, and and changing that angle of light to make that shadow go up. So the shadow's actually going to move up, it's going to slow down, and then it's going to remain stationary, and then it's going to fade out as the sun moves out of our field of vision and takes its light with it. And that's what's going to cause the sunset. So we have two mutually exclusive scenarios here. Did you want to add to that, Stone?
Yeah, the guy who did this video, the frame right in front of us, his name was Shadow Reveal.
Shadow Reveal. Thank you, sir. Thank you. Much appreciated. This is an awesome simulation. And he notes here that this simulation is not to scale. The purpose of this simulation was not to simulate it in terms of one-to-one to scale. It's to give you a visual representation of what would happen, so you can go out and test this for yourself in the real world, where the scale is the world, right? So, and the assumed mainstream figures that they give us. So to give a representation of what this looks like without playing the full video, we have the shadows. The shadow cast by these pillars was above the pillars themselves. And then we have the abruptly ending shadow here from Earth curvature that's overtaking everything. But before we have that, we have the last remnants of the window where the shadow cast by the window has exceeded the height of the window itself before it gets abruptly ended by Earth curvature. And then whereas on the flat Earth, the shadows cast on the wall here never exceed the height of the pillar casting it. And the same thing happens with the window. It rises from the ground to about up to here, and then it just remains stationary and fades out. So we'll take a clip here, a screenshot of Stone's house facing west at sunset. This is where the shadow is climbing to. And then I think this is where it actually reached its peak, like right around there. Nope, it went up a little bit. So it was coming up. It slows down right around here, reaches its peak here, and then it just, you can see where it's faded out here. Now I have a link to the full video to save time. We're not going to watch the whole thing, but highly recommend. Here's a link in the relevant chats real quick for the boys. Shout out to the homie Leland. All right. Okay, so what's observed here is a mutually exclusive proof that the celestial bodies do not go beneath your feet. And the mapping of the coordinate system and the merger of the two hemispheres to make a globe to complete the spherical coordinate system doesn't seem to have any physical representation of Earth curvature at all. So moving forward now, we'll look at another example. We have satellite orbits and circumpolar navigation. So this is mutually exclusive because of the coordinate system and its usefulness under projection and things remaining invariant, such as courses plotted on the coordinate system, as long as you use the correct correction for the projection you were transforming to, you will have the corresponding path for navigation or orbits. Oh no, we can't see that one as well. One second. That's not good. All right, well, I'll fix that in a minute. All right, one second. Okay, there we go. Sorry about that. Okay, so suppose you have a satellite that's orbiting north-south. It's going over the globe and coming up around on the other side. So here we have a satellite. It's coming from the South Pole. It's going over the North Pole, and now it's coming back. It's coming down around. It's going under the South Pole, coming back around now. So this is what this would look like if these orbits were true. If you were to plot this out on a equirectangular map, you would have these two lines indicating, you know, we're coming down over the ball. Now we're coming back up around it. These are all representing the same thing. So suppose we put that on an AE map. What would it look like? Well, you're coming up over the North Pole, and now you're coming down to the South Pole, and now you're back around coming up to the North Pole. So this is how these orbits would look when you transform them to different map projections. So we're going to take some mainstream spirographic equirectangular projections and transform them to an AE map and see if their circumpolar orbits are actually true circumpolar orbits, or if they're just making figure eights in the sky, i.e. never going below our feet and coming up around the other side. All right. So this is an example of one. So if you go to Google and type in equirectangular satellite projection or satellite orbit projection, etc., you'll get a bunch of these. So we'll take some examples of some of them and just breeze through these. So here we have a giant figure eight in the sky. So what they're doing here is they're just doing giant loops. They're not going underneath anything. We don't have these straight lines that would represent their orbital paths. We would have a series of straight lines as they complete their orbits and come back around. Actually, they'd probably be intersecting straight lines. But what we have instead is the flower of life pattern. And then same situation here. We have another orbital path for something. And then when you plot it out, figure eight in the sky. Spirograph trying to represent circumpolar navigation on a globe. Figure eight in the sky. All right, let's do one more. Globe projection trying to represent circumpolar orbit.
Figure 8 in the sky.
Figure 8 in the sky. Ah.
Another figure 8 in the sky.
All right. This one, though, for sure, is going to be a north-south circumpolar orbit, right? Figure 8 in the sky. They got us again.
Dang it.
Another? Nope. And it's endless. So there's an open challenge / if you just want to help out, any orbits that you don't see listed here, if you happen to find some, send them my way and we'll put them on the proper projection and we'll see if we can find us a proper north-south circumpolar navigation orbit. And then now we'll look at some terrestrial navigation, so planes. Okay, so we all know we can navigate east-west. That's no problem for either model. If the Earth were a globe or if the Earth were represented by a spread out map of concentric circles that get further out from a North Pole, you would east-west circumnavigation would be no problem. So when we do north-south, though, as I was showing, there would be a mutually exclusive projection. This would be only one of these maps would be, or only one interpretation of the map projection would be able to facilitate this type of movement across the terrain. So let's take a gander. So here we have the Pan Am Flight 50, where they were saying that they were going to take this circumpolar route, and this is going to be like a world record flight, and you can be a part of it, yada, yada. Let's see what they did. Oh, figure 8 in the sky. Almost. Very close. Just a big loop around a circle and not doing the actual traverse necessary to facilitate their claim on a globe. So here we have more Pan Ams. Let's take a look here. It's not a figure 8 in the sky. And we have another one here for the One More Orbit crew, the world record for the fastest circumnavigation for a globe in an aircraft. 1 second, I'm gonna grab some water here.
Who wants to place bets that this is definitely going to be just like that line we first saw? Nobody? You guys would be right.
All right. So we got their routes here. Let's see what they look like. Nope. Just a loop. Not a circumpolar route. Again, same thing. And then we have the company here saying, oh, you know what? One question about these projection discrepancies. They're like, oh, you know what? The marketing team is just showing a conception, and that's not the accurate flight planning. Oh, okay. So they're for real going around the ball, but they're showing us a not going around the ball projection. All right, cool.
Yeah, we had to fudge the route because we had to. Don't worry about it.
Sorry, our marketing team gaslit you. It is
like,
a ball.
Dude, sorry, our
hardcore.
Yeah, dude, the inadvertent gaslight. So as we move on here, just looking at all these again, they're all representing the same thing, that they aren't doing circumpolar navigation in any way. Never have, never will. And here we have a nice GIF made by Shane that's not going to show up properly in presentation mode, but if you zoom in closely, you can see it over there. That's the One More Orbit crew orbiting nothing and just doing a doing a little marketing route, I guess.
They're looping, but they're really happy about it, if you can see that. So they're really happy.
Yep. But yeah, this is what it always is. It's never not this, guys. So I had a bunch of people, I tweeted this out and I had a bunch of people try to add different ones and say like, oh, what about this one? What about the Pan Am? What about the One More Orbit? And none of them ever turned out. This is the summation of all of
give you
these.
shit about the South Pole projection? No one said shit about that?
Nope. Never.
Nice.
Never. So the next up, we would have Battle of the Beams, and I'll give a quick summary on that. In Battle of the Beams, the geographic graticule is used to establish targets based on latitude and longitude, where intersecting radar beams would be cast over an altitude of 19,000 feet, and a plane would fly in the signal of the radar system And the radar signal itself consisted of two intersecting signals that created what's called an equisignal in the mid part of the beam. So the left of center would be dots and the right of center would be dashes. And in the center, there would be a coherent tone that's created as the pilot flies through it. So you would have your transceiver set to, tuned to that frequency. And you would just hear a coherent tone as you fly through the middle of this to target, where you would be intersected by a secondary beam at a lower frequency. And when you hear that lower tone, you know that you're over target, and that's when you drop your bombs. So the thing with this is the observer height of the tower and the distances that these towers were used at, and the nature of the beam geometry to facilitate usefulness of the targeting system is only possible if the Earth is flat and there's no actual physical Earth curvature to cause any obstruction to the beam, because if there were, the radar system would not work. So the common explanations given are refraction or diffraction. If refraction's invoked, you'd have to extend Earth's radius to 15,000 miles. So instead of 3959, you'd have to adjust your refraction coefficient to make it 15,000 miles at a minimum. And then that would just be for one location. For a because this is triangulated by an intersecting beam, you would have to establish a like an equally insane gradient to compensate for the distance of the other beam, and then that would also have to somehow be the same gradient as the first beam, so that they can all intersect at 19,000 feet, which seems like a bit much. And then if you get into diffraction, like for example, if you take a look at this picture. If you imagine a radar, a signal being sent from the radar over here on the right, and it hits Earth curvature, what they're saying is that like a small portion of it will make it over this curvature. And then after it gets over the curvature, it'll start expanding outward again, and it'll just magically recreate itself. And the problem with that is like I said earlier, this radar system is dependent on a specific geometry to create an equisignal that a pilot can fly through. If this beam hits Earth curvature and it starts diffracting, it's going to create pseudo equisignals throughout the beam as it starts to expand and recombine and bounce around and do all the things that are claimed to try and make this possible on a globe, which would completely render the system useless and inoperable, because the countermeasures to the system were actually just to send a similar frequency outward, which would create pseudo equisignals that would confuse the pilots. So if there was any distortion en route, like this would be completely useless. You couldn't use this at all. So here's a top-down view of, oh yeah, keep in mind for this view here, because we're going to look at some more diagrams of some instances at distances where this targeting system was used. And this orthographic view is going to be applicable to that analysis here. So here we have a top-down view of the intersecting beams. So like I said earlier, the left of center would be dots, right of center would be dashes. The plane would fly in the center where the two beams intersect to make a coherent tone. And this is just an overview of different radar stations that were used throughout the 1941 bombing campaign by the Germans during World War II. The first system, when it was first brought online, it was the only two that were operable when the measurements were made, and this system was discovered by the British was in the summer of 1940 in June. But anyway, the only two operating stations were at Cleve and at Stolberg. One is, and they were targeting a warehouse or a airplane engine manufacturing plant in Derby, a Rolls-Royce factory, and these are the systems that they use to intersect the beams over there. So we're going to have a distance of, I think it's like 330 something miles from Cleve to Derby, and then Stolberg is about 450. So we'll go over the math on that here in a minute. But this is what the radar system itself looked like. So some people will say that, another possible explanation for this, they'll say that, this is due to sky propagation. It's just bouncing off of the sky, off the ionosphere. Or and I've even heard it asserted that they tilted the radar system, that you could adjust this to shoot it at the sky. Not physically possible with this system. It's aligned vertically and it rotates on a horizontal axis. It doesn't tilt towards the sky. Inside of the truss system. It has a dipole alignment that's set at half wavelength so that it can use the magnetic field of the dipoles to collimate the radiation pattern to a center point that propagates out with the focus of it, with like the bulk of the energy coming out directly horizontally, which I should include a radiation beam pattern here, the side view of it. But basically this is just sending out a horizontal beam. And then you can adjust the dipole alignment here to finely tune this intersection point. So you could adjust the size of these overlapping beams to change the intersecting beam here in the center by adjusting this into like a V shape or loosening it and making it like a U shape. So that's how that's the only way they could adjust it. They couldn't send it to the sky at an angle or something like that. This is just horizontal propagation. And this radar system was about, I think it was, 30 meters tall. So when you get into the highest observation point, or the highest elevation that this radar system was at like 400 something feet. So when we do the calculations later, we're going to make everything a uniform 665 feet for the observer height of these towers. And that's well above the tower specs and the elevation heights for all the instances that we looked at earlier for all the stations that were used all throughout here. So anyway, here's a top-down view of that radiation pattern with respect to the dipoles here. So this is what the dipoles are doing. It's just like as the radiation pattern's coming out, it's being refocused, like the bulk of the energy, so that it overlaps and then just gets shot out through this midpoint here, which gives us our dots and dash left and right in our intersection, or our equisignal in the center here. All right, one more look at the side view here of the radar system before we get into the issues with diffraction and sky propagation. So diffraction, this radar system was said that it wouldn't work because you would hit Earth curvature at 30 to 50 miles. And when you hit Earth curvature, you're going to be unable to use this system because of that specific beam geometry that's required for a plane to fly through it for this to be accurate. But let's assume that this was possible on a globe and it hits the Earth curvature and follows a tangent to the horizon and it becomes sky propagation, or it hits the Earth curvature and diffracts up and, follows its, continues to go out over target after diffracting. So what's going to happen here is this beam is going to be placed at 38,000 feet, but the bomber is flying at 19,000 feet. So there's going to be a discrepancy in the usefulness of that beam geometry of 18,000 feet for that equisignal. And we know the size of the equisignal because when the British found out about this system, they actually took measurements of the equisignal during the day when they flew their own planes through it. And they measured the equisignal 50 miles shy of Spalding, 50 miles shy of Derby, at a place called Spalding, and then also 50 miles to the east at a place called Beeston. So we'll look at the discrepancies there with respect to the actual measurements that the British made for the usefulness of the radar system. So anyway, they measured at Spalding, the British, that the equisignal of the beam was 450 to 500 yards wide. So, and we know the starting size of the beam was 10 meters. So we know the exact beam divergence that was from that. And it's less than a degree from tower to target at 19,000 feet. And this would only be possible if this was a horizontal beam propagating over a plane. Second. All right. So now in the next example, this will be if you were to complete the full distance to Derby, because this radar system was used for targeting, but they actually missed Derby on their bombing run because of the countermeasures that were employed. But this targeting system was used. So we'll do and not just where it was measured at for the accuracy there, but to do the full extent of the target at the full distance, that's 334 miles away. So that creates that would put the beam altitude at 60,000 feet, which creates a deficit of 41,000 feet. So as you start to run these numbers for these different potential causal mechanisms of overcoming Earth curvature, diffraction, or sky propagation, we're starting to realize that this would make the system completely unusable, because the idea was to not bomb, indiscriminately, or to not maybe hit a target. Because if you tried to use celestial navigation as a reference to do bombing, it was the most inaccurate inefficient way to drop bombs. There's a report called the Butt Report that the British did because they were all high and mighty and thought that the use of celestial navigation to do bombings was super accurate and they were like much better efficient pilots. But then from this report, they found that the Germans were actually like, surgical precision, and the Brits were like, missing everything and had, no targets completed. So there's the usefulness of this system is, speaks for itself. It wouldn't have worked on a globe if the beam had to be interfered with. So here we have the distance from Beeston. This is on the other side coming to the Derby site. So measured at 440 miles away, there would be a discrepancy of 92,000 feet because the beam would be 111,000 feet over target. And it just gets worse from there. And then here's what was actually used and measured. And all the angles comport to a plane flying over a plane through a radar beam that's propagating horizontally over a plane. And all the angles used match up to the angle that was measured of the equisignal over Spalding by the British. So everything corresponds to it working on a plane. And then to add salt to the injury here, we have the Telefunken company who built the radar system and tested it before the Germans used it, and they were flying at 13,000 feet and went up to distances up to 1,000 kilometers and were able to maintain useful beam geometry. And I think, let's see, what was their, can't remember their specs, but the beam geometry was sub 1 degree there as well. So still accurate and useful. At no point is it hitting curvature and, being obstructed or anything like that. So we have the arctan which is the angle from the radar system to the plane over target. And this is 0.2918, just not even a full degree from the, like in terms of elevation from target to the radar system. And if we were on a globe, like these angles would be different. They'd have to be different. All right, so everything is comporting to, actually doing cosines. We're getting the angles that match the beam measurements. So unlike the other scenario where you follow the cosine and then your measurements off and you assume that it's due to ball curve, we're actually dead on and make the correct angles for everything that correspond to the tech specs and correspond to what was actually measured using plane trig. So after that, we have so real quick recap on that. The coordinate system that was used to do these bombings to reference these targets was just the latitude and longitude of the target. So using this spherical coordinate system, they were able to use intersecting beams and line of sight targets that were, 300 to 600 miles away with pretty good accuracy. Like much better than the British. But like I said, it was easy to spoof it out because the downfall of it is if you sent a signal in at the same frequency, it would just create pseudo echo signals. So, there can't be any Earth curvature obstruction because they flew them in that way. If that was happening, they wouldn't have been able to even get the target to be useful. Next up, we have the Selenelian eclipse. So any questions so far yet? I've been through a lot of stuff. Anyone got any questions so far?
No, you're killing it, bro.
Awesome. All right. So we have a celestial phenomenon happening above the horizon that's said to be occurring below the horizon, but due to refraction, which is just making the optical phenomenon equivalent to happening on a plane. So co-opting our position that all celestial phenomenon happens above the horizon. This is proof of that. And we have the eclipse coming down at the wrong direction. The shadow comes down top down instead of bottom up, like it should be if this was the accurate representation of what's happening. So in the Selenelian eclipse, the sun and the moon are in the sky at the same time, and Earth is said to be casting a shadow on the moon during that time. But they're saying that due to refraction, you actually see these bodies, these apparent bodies, you see them double extra apparently, and they're above the horizon while this happens. And it's like, okay, if that were true, if that position were tenable, then the shadow would at least go bottom up, right? Like you would at least have that for geometrical purposes of your argument. But that's not even the case. It goes up opposite. So what you saw was the shadow coming top down. What you should have seen is the shadow going bottom up. This is mutually exclusive to the interpretation that is put forward here by the mainstream that says that this is due to a celestial phenomenon occurring below you and you're able to see it above you. That doesn't track. Right. All right. So next we have
Impossible eclipse.
Right. Yeah, they literally call it the impossible eclipse. And it's like, why is that? It makes no geometric sense in their model. Calling something impossible and parading it around as proof of your model is not proof of it. So this is now evidence against it. All right, so now we have the 24-hour Antarctic sun. Now, some people, like myself, predicted that there would be no 24-hour Antarctic sun, and I'll propose a mechanism at the end of this. This is just speculation, though, so like let that be noted. But anyway, I'll present that, my thoughts on it. But we're going to analyze the new data point. So the elevation angles all comport to a flat Earth. There's no difference in seeing something above the horizon. Like in other words, a celestial phenomenon occurring above the horizon doesn't help prove Earth curvature in terms of it's not, you can't falsify the planar position by a celestial phenomenon happening above the horizon. That doesn't track. So the fact that this occurs, while not expected under certain assumptions and models presented by myself and others, it's not a falsification of the position of the Earth being planar, because as we've shown throughout this, there is a massive discrepancy in geometric properties that would be necessary if the Earth were curved. So we would have the Selenalian eclipse would look differently. Shadow sets would occur differently. You wouldn't, Battle of the Beams would have went differently, etc. Right. So let's see. All right. So again, my argument would be that the sun we see is an apparent object in the sky. Now, real quick, this is evidence. I would consider this like this would be a point for the globe, right? I don't have any problem saying that. So in the analysis, right, this would be one that would give an explanation, because their explanation would just be you're upside down and you're looking at it from the bottom of a ball. So they do have an explanation here for this. But as shown earlier, it would be illogical to throw everything out. It would be, a hasty generalization, an all or nothing fallacy, et cetera, right? We're looking for a falsification of a null hypothesis through sigma confidence. So we're going to need, more substantiation, more mutual exclusivity to even entertain the idea that this couldn't even be possible on a flat Earth. And therefore it's falsified just because of that, right? Just because there's no immediate answer for it. Okay, so again, the objects in the sky are apparent. So I just kind of wanted to reiterate that. I got several slides that we already went through there. And we got the several fallacy slides that I was just kind of covering about making hasty generalizations about one data point and how that can be fallacious, how you have to have a preponderance of evidence presented through a null hypothesis, do a statistical analysis, etc. That would be the way you would actually handle it if you were trying to do this in a meaningful way. Let's see, the next up would be the Eratosthenes Earth circumference being measured through sticks and shadows. And what they do is they take an angle of a shadow during the midpoint of the day. And this, when you convert that into, or when you divide that angle over 360, you get 50, which you multiply by the, can't remember. Oh, the distance from the two locations that you're taking your shadow measurements, and then that will give you your circumference, right? Now, as Shane showed, this gives you your optical limit of vision as well. So this is, you could do this anywhere on Earth, and it'll tell you, it'll give you that information. The only thing that is the only difference between a flat Earth and a globe Earth with this calculation is the assumption of the distance to the sun. It's the only thing that makes the defining factor here, is just assuming a distance. So when you use a local
distance from the same angular size anyway, so that's a non-factor again.
Right, all based off of that same half a degree angular size that we went over earlier. So yeah. So when you have a local light source, you can achieve the same shadow discrepancies, and you could import the same numbers and get you can make this table curved if you want through math, even though it physically doesn't represent any curvature. You could then, start doing trigonometric functions based off of lights in your house to, tell where you're at on this spherical table. And then my boy Cryptotosthenes, he was actually Eratosthenes' brother. And he was wondering if anyone's ever witnessed a Selenian eclipse, because that shows that celestial bodies don't go below your feet. And he's actually really mad at his brother for telling his brother Eratosthenes for telling everyone that the Earth is flat or curved, because he measured shadows and assumed that the sun is hella far away. So you can see here he's looking off into the distance very stoically. He's very disheartened with his brother's choice and assertions. All right. So now we have southern star trails. So star trails in the north versus the south in the counter rotation. It's mutually, they'll say that this is mutually exclusive to a globe and being on the other side of a globe. So you're going to see it counter rotate. This is what it looks like at the equator. My take on this is that we're seeing a northern star field and a southern star field, and they're diverging at the equator. So the way I conceptualize this is that this is representative of toroidal geometry. And what we're looking at is two star fields that are diverging, one for the north, one for the south. And all celestial phenomenon is going to have their corresponding convergence point, where you're going to have a midpoint for that rotation there. So here's like so this would be like the bottom down view looking up. This would be a top down view of the same thing. This is what you would see. And we have our boy No Fanfare here. I'm not going to play out the video, but I'll put the relevant link in the relevant chats here real quick. All right. Oops, 1 second. Okay. So anyway, what he does here in his model is puts the observer inside of the dome, and then you can see the stars going in opposite directions. Definitely check out his video on that. So no mutual exclusivity over there. This would just be a function of perspective and the geometry of the star field. How you perceive it. Even you wouldn't even have to take it as far as I'm internalizing it, right? It would just be, you could just argue it on perspective alone. So how do I think a 24-hour sun could work in the Antarctic? So as I divided up the two hemis into two physical star fields, and then we have a dome of vision within that. So how we're going to see in these two star fields is going to be basically represented by curved visual space. And the fact that we all see the sun as an apparent object in the sky, when you're in the southern lattice and you're seeing the sun arc towards you at your local solar noon, you're seeing, the apparent sun with its GP that's represented between the tropics. And then as you pass solar noon, you see it arc away from you, still following the GP in the tropics. But to do that, the sun has to completely wrap around you. And I don't think, or in my cosmology, there's nothing beyond this point in the south. And when you get here, your spherical limit of vision, everything, all the celestial phenomenon that occurs wraps around you there so that you're still in the center of creation, and you could always reference it to get back to the north. So that's how I conceptualize it. That would be how I answer it, is that you're always seeing an apparent object and they're wrapping around you. The antarcing of it corresponds to the change when it passes your local solar noon, because that's when you see it in the south go from arcing to antarcing, whereas in the north you would always see it arcing. So I think it's just perspective based, and I think that that's the edge of the world. So that's just what I believe for it. So, like, feel free to disregard it, or that doesn't matter to me.
I dig that explanation. This is the end, dude. It's gonna turn around. But if you couldn't see the way that you've been seeing, how would you navigate to get back, right? Because the stars are put here for us to navigate, for us to denote. So if they took them away when you went out there, you could never get back. That's such a weird argument.
Yeah, that's just kind of how I've been thinking about it. Some people are like, oh, there's more land, there's other stuff out there, but it's like everything that we kind of know, though, is like in relation to the stars, and it's all in this general area that comports to a specific way. So, like, I just don't really know how that fits. So anyway, like I said, that's just my personal interpretation. Feel free to not use it. But also there's the promising model that Joe Hanvey's doing. So hopefully we're looking to see some additional observations done by him where he can put the camera inside. And I forget the other one that he was going to try out as well to make it more analogous to what we're putting forward. Submerge it. Yes. Thank you, sir. So submerge it and put an observer in the dome so we can see what's going on there. That would be awesome. But yeah, there's possibilities out there. When you approach this with a analytical level and going through, the mutually exclusive points and not getting caught up on everything that's equivalent and just narrowing it down between the mutually exclusive stuff, you can start to build an analysis where your null hypothesis is supported and the reason to reject it in favor of the alternative hypothesis is, it's just not there. And like I said, this will be further refined and written out in a more explanatory, exact way so that it can be disseminated, and analyzed for everyone. And it'll include the sigma analysis and look more professional and whatnot. But for now, it's just a prezi for the boys to just kind of remember what we're doing here, So if anyone has any questions, comments, or wants to add anything, hit me up.
Great picture of that Selenilion.
Yeah, it's a doozy.
Did you show the diagram of how ridiculously far around the other side of the Earth the sun's supposed to have to be?
This one?
In their model for it to work. Like they say the sun has to be underneath the Earth on the other side in order to project the shadow the way it does.
Yeah, are you looking at the thing?
Yeah, I see it. I'm saying that sun, that bottom sun.
Yeah.
In their model, it should be below the Earth, like where the word atmosphere is. It should be like where the word atmosphere is.
Oh no, I haven't seen that diagram, but yeah, it's ridiculous.
Well, that's where it'd have to be to project that shadow.
Nice.
Am I the only one not getting the video?
Did Alan stream in 1080p again?
I did, but at 30 FPS.
I have no idea, but I've closed out the application. I've restarted a bunch of times. I can't get, all I get is the dancing blue squares.
You effectively ruined Ken's whole presentation, Alan. I hope you're happy with yourself. And your
Those two Selenilion pictures are worth sharing, just the images, bro. Freaking great.
Done. All right, let's check the boys in the chat and see what they've been up to while I've been presenting.
Can I get the diagram?
What's that, Meow? Yes.
I'm sharing with my boys. Thank you, sir.
Yeah, great Prezi, Alan. I'll catch you guys later.
Later, bro.
Bird.
That was
All right.
excellent. Thank you.
Yep.
Hey,
Cool.
Alan, did
Like,
those last images you had of like the toroid of the dielectric and magnetic field, is that what Sam had put together?
I'm not sure. I think this is an old Shane picture.
Oh, it is?
Yeah, this is the so that
yeah, no,
there was
that's a new Shane picture. I was trying to diagram what the hell happened.
yeah, there was a simulation from FE Core where they simulated the position of the sun for all observers on Earth, and it basically makes a giant toroid. And so this is kind of an overlay of that apparent toroidal geometry mapped out for an observer at every latitude, and then overlaid over the actual toroid, showing where the sun would be on the curves of that toroid.
Yeah, well, and I remember there was a guy, you guys, I think it was I Can Science that did some images as well. That I think it was him earlier. That stuff was super cool too, but I was just curious because that's something that's been talked about a lot recently, was that exact image. I don't know if you're opposed to it, but maybe dropping a link to where I can find it.
I have no idea. Did you just want the link here?
Yeah, if you wouldn't mind, maybe just putting in the main chat or whatever. I'll
The links to
from you.
the links to the images?
Yeah, to those last two images, the one with the dielectric and magnetic field.
I
Yep.
got you. Hold on.
Gotcha. They're in main chat.
Here's the main
Cool,
one.
thank you.
Yes, sir.
The one that I drew on. We stole that from Psycho. I forget. I just call him Corpus.
Dude, the Celine Dion eclipse. Thank you so much, Shalom Shire Farms, for calling it that. I totally forgot that I was going to rename it the Celine Dion eclipse. So, henceforth, it is the Celine Dion eclipse.
Hey, Mister, I'll give you the Canville link so you can play with that if you want. So yeah, so that was awesome. I love how you steelman like 4 of my presentations all at once.
Dude, it became dude, a lot of
together
yeah, a lot of that really fell together, especially with the Aries thing, when it was like, oh my god, your whole model is built
With,
on
like, the final
cosines
piece,
and
the-
parallel lines. Like,
Dude, the
why
final
doesn't it
thing
work?
together. There is
Right?
no Zenith. There is no ground position. What the hell are we doing then?
There is no Zenny, dude. It's all just a model and a map reference to stuff in the sky based off of an elevation angle to a star.
It's a linchpin that look, when we take a cosine of that angle to the star, we know it's real because we can go under that star and we know how far when we measure it. Well, no. Nope. Never actually got that far. Still just calculating stuff on the ground based on the sky.
Dude, well, think about this, right? You did the conversion for an arc second to a distance, and for those one corrections that they were doing in Australia for just the 6 arc seconds for the deflection of the vertical, that's a distance discrepancy of like, what was it, 568 feet or something?
You know, if you tried to pass off the outer, larger concentric circles on a flat Earth as symmetrical as in globular theory, you would have issues in the south, particularly. So, like, lo and behold, all the gravipotential issues happen in the far south. Like, Australia is notorious for having
30 arc
wobbly,
seconds, bro.
like all
30
over the place. It's crazy. I wonder why.
30 arc second corrections in the Australia, bro.
Mm-hmm. They have specific geodesy papers about like, oh, the Australia anomalies. It's like notorious.
Yep, shout out to the Aussie lads. I'm relieved that they're not
all fucked up
antipodal.
maps, dude. All their maps are fucked up because all their surveying is like, man, pulling that plumb bob all over today. It's pulling it left and right. Left, it's right.
Oh man, the gravitational potential is killing me today. All right, well, I'm going to link the Discord here. You guys are free to join. I'm going to wrap up the Prezi here. And we'll call it a day. So I'll be presenting this again on Earth Awakenings on Saturday at 10 p.m. Eastern, and then Friday will be, of course, Flat Earth Fridays. And I think we'll do research and reading tonight, or Thursday, maybe. We'll see. All right.
Plus a little thingy going on just before on Friday night, right?
Dude,
Right,
thank you.
right.
Good call, Stone. My bad. Totally forgot. Sorry. Man of Stone, there'll be the world premiere of a new Man of Stone video on Ares failure. He's going to do a little stone analysis for us, and I'm hoping that there's some music involved, as Stone has been known to be very musical. And then
quite a bit of music, and that'll be 8 Eastern here.
Nice. Right here. 8 Eastern on Friday. Nice. Right before Flat Earth Fridays. And then
well before, probably.
Yeah.
I'm looking forward to that. That sounds like fun.
Me too.
It's going to be awesome. And then on Tuesday, Gregory from Earth Awakenings is going to be presenting on logic and fallacies. So our resident our resident Bruce McGuire Galatrax has been telling me of the tales of Sir Gregory, and he linked some of his work on fallacies and whatnot, and I was just really impressed with it, and I'm super into logic and applying that to debates and stuff. So anyway, he's going to come through and do an awesome presentation on logic and fallacies. And for the record, personally, I have never seen Galatrax and Bruce McGuire in the same room at the same time. Not making any claims.
Yeah, except that I do a better impression of Bruce than Gal does, so debunked.
Here's the thing. We know that he hides his voice through a voice modulator on his channel, and I think that Galatrax is using his real voice with us, and he's using the fake voice with Bruce. All right, see you guys later in the week. Peace.
What I'll need to make some coffee now.
Oh, Lily, where can we go to get coffee if we're parched?
Oh yeah, I was just about to go make some coffee. It's this wonderful brushtail coffee, and I guess I haven't shared this one very wonderful testimonial with people. So I'll tell you guys, I have this very rare medical condition where if I was really excited and if I was really happy and it was also like something funny that someone said, it's a particular combination of different emotions, because as you know, different emotions create different neurochemicals and neurotransmitters in the brain, which is different electrical frequencies, really, because it's all about electrical frequencies. And so they're bioelectrical frequencies. Anyway, long story short, not to sound too sciencey, but I had this rare medical condition called hologrammatitis. And so what happens is that when I get excited and happy and something's funny all at the same time, I turn into a hologram. And so, yeah, and there was no cure for it. And then when I started drinking brushtail coffee, I have been cured. So there's hope for anyone else out there who has hologrammitis. Thank you. Brushtail coffee is the answer. It is so good. It's so tasty. Right now I'm drinking the one from Mexico. Oh my God, why am I forgetting which one it is?
Better than stem cells.
How what?
I said better than stem cells.
Well, the Ethiopian one's really good too, and the Tanzania one was very good too. So, folks, try out brushtail coffee, because I know that it cured me of hologrammitis, because now I don't have it anymore. Isn't that great? All right, thank you.
Dude, you're awesome, Lily. Thank you so much. Shout out to brushtail.coffee. where our boy Toby makes the freshest coffee in town. And shout out to Toby. Sabine Hoffensfelder finally released him from her clutches, and she let him go. Basically, he was rescued, and he is returned to us. Thank you for returning our Toby. And to play us out, we're going to watch a Man of Stone video on the climate asymmetry in the north and the south. So,
Oh, splendid.
yes. So this will be added to the arguments as well, because if the correct interpretation of the graticule is the azimuthal equidistant map, there's not going to be symmetry in the climate in the north and the south because there's going to be a distance discrepancy, which could be, I don't know, covered up through all these deflections of the verticals to the tune of 30 arc seconds, which would be, I don't know, like, what would that be? Like 2,500? I don't know. It would be a lot. So anyway, we'll watch the Man of Stone video on the north and south pole. Tilted than I thought.
Defeated by good old symmetry yet again. Foiled. Gets him every time.
Awesome, dude. Thanks, Stone. Much appreciated. You're always crushing in the background, brother, and in the foreground too.
Yeah, I'm gonna steal that one right now. Actually, I haven't stolen that one before, so thanks.
That's a new one. You gotta get your
More power
paws
to
up.
you. Yeah, go get it while it's oh wait, it's a couple years old, isn't it, boys? Yes.
All right, lads and ladettes. Merry Christmas, happy pagan holidays, happy all that stuff. See you guys